The inductive effect. So the word inductive means to pull, right? It tells you something about pulling electron density in this case. So inductive, again, to pull. So let's look at these two examples. It says here the acidity of an acid increases in the presence of atoms more electronegative than carbon. So again, we're looking at more electronegative atoms than carbon. So these could be F, Cl, O, N, of course, Br, etc. So we're looking at some of these atoms. If you compare the pKa's of these two, the pKa of this case ethanol, it would be around 16. It's an alcohol, but the pKa of this molecule is around 12.4. So how can you explain the difference? So obviously you know that this one right here is the stronger acid. So the question is, how do we explain that? How do we explain that? So what happens is that we say electronegative groups such as halogens increase the acidity of the nearby acids by stabilizing their conjugate bases. So the only way we can understand this is by actually drawing the structure. So let's draw the structure. So you have, can say the CH3, we have a CH2, we have an O, and we have an H. Now, again, we're trying to draw the conjugate bases. So when we draw the conjugate base, it means we remove this proton. So we're going to have a negative charge on it. Now let's draw the conjugate base of this and actually show it. So we have C and now 3 fluorine atoms. So what is happening here? Well, what's happening here is you actually have these fluorine atoms. These are more electronegative. So the electronegativity of fluorine is 4.0. The electronegativity of the hydrogens is a 2.1. So the electronegativity pulls electrons. It pulls electrons away through these, you can say, through these single bonds toward the F atoms, the fluorine atoms. So these fluorine atoms are drawing electron density toward it. So the fluorine atoms pull electron density from the negatively charged oxygen atom. So if the oxygen becomes, so if the oxygen, I'm going to write it under here, oxygen becomes less negative, which equals more stable. More stable means less basic. And of course, less basic means more acidic. So, okay, you see the patterns here. So I need you to, again, keep these trends in mind, right? So more stability means less basic, and less basic means more acidic, which explains the pK right here. So you couldn't do that just by, again, with general chemistry ideas. So in the, when we look here, so let's look at the inductive effect more broadly here. We have a carboxylic acid derivative here, and we have X. Now, X could be any of these atoms or groups. That's all we're saying here. And we want to look at some patterns here that are going on. Now, again, looking at the acid is not going to do it. So what you need to do is you need to draw the conjugate base of this. Draw the conjugate base. So where are we going to remove that H from? It would be from O, because oxygen would be more electronegative than C. So you would actually have with a X. Now, what happens is, again, with the inductive effect, is that the whatever X is going to determine the extent to which the electron density on oxygen will be pulled toward it, and thus stabilizing the oxygen. So again, if you have atoms that are different, they will have a different pull on this electron density. So let's look at the pattern here. We notice that the pKa goes down when it's more electronegative. So with H, it's only a 4.76 as a pKa, and now again it becomes, we see here that with increasing electronegativity, so the electronegativity is increasing, we notice that the acidity is increasing. It is increasing. Okay, so the acidity is increasing. Now, we will get to learn about these later in the semester, probably more in organic too, but you notice that they also have a difference on the pKa. Of course, they don't have electronegativity values because they're not atoms. So electronegativity only applies to single atoms. But again, you see that the pKa is being impacted. So these are also, you can think of them as what we call them electron withdrawing groups, or we simply call them EWGs. So here's what you need to remember is that as X gets more electronegative, a stronger pull on electrons occurs. That results in O will become more stable because, again, there's less electron density. Once again, we're spreading the charge right here. So of course, that results in, again, the conjugate base will be weaker. Therefore, this is going to result in a stronger acid. So that's the idea that you need to associate. The stronger uh, the more electronegative the atom will be, the acid will be stronger. The stronger the acid will be. That's what you need to think of. So if we look at another aspect here that's important, and that is one more before we go on to the next two, they're actually quite simpler, is that the distance of the electronegative atom from the negative charge is important. So what happens is that if you have electronegative atoms that stabilize the regions of high electron density by the inductive effect, it happens to actually decrease this inductive effect as the electron withdrawing group gets further away. So we see that in this example that's right below you. If you look at the example that's right below you, that's right in front of you, you'll notice that the pKa's, and let's actually write down pKa's. The pKa of this is about 2.97. Notice how far away, notice how, or its location to the oxygen, this oxygen right here. Notice how that second one actually now, the bromine is moving farther away. And in this one, it's even moving farther. And then in the last one, it's moving the furthest or the farthest. It's actually farthest, not furthest. So the farthest it is away, the weaker the acid will be. Again, the pull simply becomes weaker and weaker. That's the idea.